Good afternoon, pilot teachers, and good afternoon, students. Thank you. Sit down. Okay, we're going to actually move on to looking at the different ways in which contributes to why temperature varies from one place to the other. We started off with the introduction to the work on climate by looking at the definition to what climate is. And we said that climate is generally to do with the average conditions of the atmosphere over a longer period of time. There are three important factors that contribute to what makes a climate different from one place to another. And those three important factors are temperatures, pressure, and precipitation. We started off by looking at temperatures, and with temperatures, it is simply to do with the energy from the sun heating up the surface and the heat that is actually insulated through the process of insulation that contributes then to the warming up of our surface. We looked at solar radiation, and this is revision from what we have covered. The incoming solar energy from the sun is actually absorbed, reflected, and scattered. 50%, about 45 to 50% of the solar radiation does reach the ground or the surface. And from that 50% then is used to heating up the air or the atmosphere around us. The heating of the earth can be done through the process of radiation, conduction, and convection. And from our last lesson, we looked at what each of those three different processes involved. Radiation was simply to do with heat waves sent out by the Earth's surface. Conduction, mainly to do with passing of heat by contact. And convection, simply passing of heat by air currents. We also looked at some of the factors which contribute to what makes temperature different from one place to another. And we had time to look at least 2 out of those 9 factors that were listed. From the 2 factors we looked at in our previous lesson, we mainly concentrated on latitude and hotter by day, cooler by night. Let's revise on what we have covered on latitude. And I'd like you also to remember perhaps a basic and a simple rule to show the relationship between latitude and temperatures. When we talk about latitude, we are basically looking at distance from the equator or the distance away from the equator. We note that around the equator, the sun's rays are almost vertical. As a result of that, heating is actually concentrated to a smaller area. The outcome then becomes that smaller area being intensively heated will mean the temperatures are higher. As you go towards the north and the south pole or the high latitudes, what happens then is the angle of the sun then is not vertical. What happens to the angle of the sun then is that it is at a low angle as it comes in contact with the surface. And because of the low angle of the sun, what then happens is that the area that is heated is a little bit more larger. The intensity is actually lost. Therefore, the temperatures away from the equator then become cooler. So a simple rule that one might remember with, not altitude, but latitude and temperature will be the further one goes away from the equator, the cooler it gets. Or in other words, we can say as latitude increases, temperatures decrease. Okay, perhaps you could make note of that, and that could be a simple rule for you to remember on remembering relationship between latitude and temperature. The higher the latitude, or as latitude increases, temperatures decrease. We also looked at temperature variation in the course of 24 hours. And from this particular example, we looked at hotter by day and cooler by night. We note that during the day, the sun shines directly on the Earth's surface. Therefore, all those areas that are in daylight would be a little bit more warmer compared to those areas that are in night. So therefore, we had a graph, and from that graph, it showed us generally what happens to temperatures during the day. We also found out that the hottest time of the day is not usually at midday, rather it is mid-afternoon. And then the temperatures decreases until we come to the night. Just at the start of dawn, the next day, about 6 o'clock, we look at the temperatures being the coolest. And then if we continue on with this particular graph, you would have seen an increase again, a similar trend to what is actually shown on this side. Today, we are going to move on to looking at two more of those factors which contributes to what makes temperatures different from one place to another. We'll start off by looking at hotter in summer, colder in winter. The concept or the idea is very similar to what we've looked at on hotter by day, cooler by night. But this time, instead of looking at day and night, we are looking at the seasons, summer and winter. Let's see if we can pick up the similarity between hotter in summer and colder in winters with what we have covered on hotter by day, cooler by night. So the third factor now that may contribute to variation in temperatures would be because of the Earth's tilted axis. We know that the Earth is tilted on its axis along the horizontal plane. It would be at an angle of 66.5 degrees. Along the vertical plane, the tilt would be at an angle of 23.5 degrees. Because of the Earth's tilted axis, the northern hemisphere receives much more solar radiation in June and July than the southern hemisphere at that same time. In other words, when it is June and July, it is summer in the northern hemisphere. In the southern hemisphere, it will be winter. Therefore, a lot of the solar radiation would be concentrated in the northern hemisphere in those months, June and July. It is hotter than in the northern hemisphere. The opposite can be said about the areas in the southern hemisphere. The sun's rays are almost concentrated north of the equator, and the days are actually longer there. At the same time, the southern hemisphere receives less energy, and the rays strike at a low or lower angle at the southern hemisphere, and the days are shorter. As a result of that, in summer, we would expect that those areas that are experiencing summer would be hotter than those areas that are experiencing winter. So the concept or the idea should be very similar to what we have done on hotter by day, cooler by night. Anyone with any queries or questions with regard to that particular factor? Hotter in summer, colder in winter. Any questions on that one or on that factor? No? Okay, let's look at the information presented on a diagram. And this diagram here we have seen already when we were looking at the revolution of the Earth around the sun. We have already come across this diagram. And this particular diagram basically shows us in June and July, The lighted area, you can see more of the northern hemisphere is actually lighted. The North Pole is closest to the sun. The area in the northern hemisphere tend to be a little bit warmer compared to the southern hemisphere. When it is summer in June, July in the northern hemisphere, it is definitely winter in the southern hemisphere. Here, 2/3 of the total solar energy is concentrated within this section of the Earth, the northern hemisphere. The days in this area are longer, and there is more direct solar radiation towards this region. It is the opposite in the southern hemisphere. 6 months later, it will be December to about January. Things are therefore reversed. And the southern hemisphere this time receives its summer, while the northern hemisphere has its winter. This information we have already covered when we were looking at the revolution of the Earth around the sun and the seasons also. Okay, if we have to look at the diagram to illustrate that, 6 months later, you can now see the northern hemisphere in the dark, especially the North Pole, and the southern hemisphere exposed. This time, it is December or January. We have 2/3 of the total energy from the sun is actually concentrated in the areas towards the southern hemisphere. The days here are longer, and there is more direct solar radiation. Therefore, the season then is summer in the southern hemisphere. It is winter in the northern hemisphere. So around this time, these areas here will be hotter. These areas here will be colder. So one of the factors that we are working with is hotter in summer, colder in winter. We're clear with that information? Okay, if we are clear, then we are going to move on then to the fourth factor. There are no questions? Okay, let's move on. The fourth factor you will also find in your booklet, Introduction to Climate. And the fourth factor then has to do with altitude. We have looked at latitude, and latitude is to do with the distance away from the equator. Altitude is to do with height. So when we talk about altitude, we are making reference to height above sea level. One of the simplest and the basic rule that we need to remember about the relationship between altitude and temperature is, as altitude increases, temperatures will decrease. Can someone put that in simple terms? If you had to explain that in your own words in simple terms, could you come up with a statement that will explain as altitude increases, temperatures decreases? In simple terms? Gideon? Microphone, please.
The higher you go above the sea level, the colder it becomes.
Okay, very good. Here is in simple terms. From what is understood, the higher up we go, the colder or the cooler it becomes. That's the same as looking as altitude increases, temperatures decreases. Okay, if we can understand that in simple terms, then we move on. So the fourth factor now that we are going to look at is altitude. And here, as already mentioned, hotter at lower altitudes, colder at higher altitude. altitude is to do with height above sea level. As one passes through the atmosphere, and to pass through the atmosphere, you will have to go vertically, you have to go up. So as one passes through the atmosphere, temperatures become colder as the air becomes thinner. It normally becomes colder by 6.5 degrees Celsius for each 1,000 meters you rise. Or if there is a 1,000-meter rise, definitely the temperatures will decrease by 6.5 degrees Celsius. So perhaps in your note-taking, all you should put down is that for every 1,000 meters we rise, temperatures decrease by 6.5. That's an important information that you need to remember in terms of altitude and temperature. Okay, we've got that note down. Every 6.5 degrees Celsius, every 1,000 meters that we go up, there is a decrease of temperature by 6.5 degrees. Let's look at an example here. This example is taken from in a calm, dry air, whereby temperatures decrease by 6.5 degrees for every 1,000 meters we rise in altitude. So if we look at an example, we have the sea level. At sea level, the temperature is at 25 degrees. By 1,000 meters, we go up, we come to about 18.5 degrees. If we go 2,000 meters above, 12 degrees Celsius, 3,000 meters, 5.5, 4,000 meters, negative 1 degree Celsius. At 5,000 meters above sea level, negative 7.5 degrees. And then at 6,000 meters, we go up negative 14 degrees Celsius. If we have to use our calculator and double check, you will note that for every 1,000 meters we are going up, there is a decrease of 6.5 degrees Celsius. That's an important statement we need to remember. Here is also something that we need to consider when we are describing temperature. Any temperatures that are actually above 20 degrees are considered to be hot. So if we are in Port Moresby and we read from the thermometer, the reading says that it is 25 or 26 degrees Celsius, then how do we describe the temperature of Port Moresby? It is hot. Now we are experiencing the cool times whereby we feel that the places are not as hot as it used to be. The temperatures come down to about 27 in Port Moresby, and everyone is saying, oh, it's cold. As long as temperatures are above 20 degrees, we give a description as hot. Temperatures falling between 20 to 10 or in between 10 degrees Celsius and 20, that is when we use the term warm. If the temperatures are between 0 degrees Celsius and 10 degrees, then we can say it is cool. If the temperatures are between 0 degrees Celsius and negative 10 degrees, then we say it is cold. Any temperatures below minus 10 degrees Celsius is said to be very cold. And sometimes in Port Moresby, we say, oh, it's very cold. So if we are looking at this classification here, then perhaps it would be wise also for us to be using the correct terms to describe the temperature. let's do an exercise. And that activity is to do with altitude and temperature. What I'd like you to do is to use your calculators, and I'd like you to calculate the change in temperature from the diagram shown for each height above sea level. We already know from what we have looked at that for every 1,000 meters that we go up, temperatures decrease by 6.5 degrees. So your task now is to calculate the temperature at each of those heights that will be shown on the next diagram. You made note of the activity? Okay, let's look at the diagram. You have a diagram there given. You can sketch the diagram into your exercise book quickly. On the left side, you put in height in meters, starting from sea level here up to 6,000 meters. And then on the right-hand side, you put the temperatures in degrees Celsius. And you are looking at the height plus the temperatures from here to the top. You are not going to be able to start unless we do the first temperature, which is the sea level temperature, and then from there you will be able to calculate. Okay, at sea level, if, say, we are at Port Moresby, at sea level, the temperature might be, on a particular day, 32 degrees Celsius. So if it is 32 degrees Celsius at sea level, perhaps here at Port Moresby, can you calculate what the temperature will be at 1,000 meters above, 2,000, 3,000, 4,000, 5,000, and 6,000? Okay, you do the calculations, use your calculators, and then we'll get you to, or we'll get the students to give the answers shortly. It should take you only 5 minutes because we are going to use our calculators to come up with our answer. And if we don't have calculators, we can definitely do the calculations to come up with the answer also. Got the answers? You can still do the calculations without your calculator, so do that quickly before we correct. Okay, most students have got the answer, so we will check. We'll start from Val and we'll go around this way with the answers. Okay, Val is going to give the 1,000 meters. If the sea level temperature is at 32 degrees Celsius, and we know already that for every 1,000 meters, there is a decrease in 6.5 degrees Celsius, what will be the temperature at 1,000 meters?
25.5 degrees Celsius.
Okay, the rest of us check. We happy with 25.5? Okay, good. 25.5 degrees Celsius is the answer. 2,000 meters.
19 degrees Celsius.
19 degrees Celsius. We happy with 19? Okay, good. At 2,000 meters, it will be 19. Gideon? At 3,000 meters?
12.5 degrees Celsius.
12.5 degrees Celsius. We happy with 12.5? Okay, double check. Give yourself a tick if you did get 12.5. Elsie, at 4,000 meters?
6 degrees Celsius.
6 degrees Celsius. All happy with that? Yes, definitely. At 4,000 meters, 5,000 meters.
Negative 1.5 Celsius degrees.
Negative 1.5. Negative 1.5. The class does not agree with you. Do you want to double check on that answer?
Negative 1.5.
He's still saying 1.5. Okay, we get somebody else to give the answer. Shelley, what is your answer for 5,000 meters? You have not worked it out. You have not worked it out. Okay, Christopher, what's your answer for at 5,000 meters?
Negative 0.5 degrees Celsius.
Okay, 0.5 or 0.5. It's a negative 0.5 degrees Celsius to be our answer for at 5,000 meters. Have you calculated for 6,000 meters? Francis? No? Your answer then. What is the temperature at 6,000 meters?
Negative 7 degrees Celsius.
Negative 7 degrees Celsius. We happy with negative 7? Yes. Okay, we double check. And yes, definitely it's negative 7. If we had to go up to 7,000 meters, then what would be the temperature? Catherine, if we had to go up 7,000 meters, what would be the temperature then?
Negative 13.5.
Obviously, yes. So for every 1,000 meters we are going up, the temperature is decreasing by 6.5 degrees Celsius. We happy with that then? Okay, we move on. We are looking at the relationship between altitude and temperature. It's also important for us to note that from what we have covered on insolation and also solar radiation, the amount of heat that comes through that heats up the surface, we note the air around us and our atmosphere is heated mainly from the surface, and heat is radiated, conducted, or convected back to heat up the surface. Along the way, when that heat is escaping, if it's coming from the surface up, what will happen is that because of the amount of water vapor and the dust content in our atmosphere, the heat escapes slowly from the surface going up compared to if we are at the top of a hill or a mountain at a higher altitude, whereby the air at the top is a little bit more rarefied and it contains little water vapor and dust. And the heat at the top tends to escape a little bit more faster and quicker because nothing is there to trap it down. That is the reason for why sometimes people wonder, why is it that the high mountain areas, they are supposed to be closer to the sun because of the higher up they are, but it is cooler at the top compared to the bottom where it is warmer. Are you following? Okay, and this diagram basically will explain about that relationship or the reason for why it is cooler at the top of the mountains or higher up compared to the surface or at sea level. On this particular diagram also, there is extra information that has been put there, and this extra information just also explains a little bit about pressure and the air and the areas of high pressure and areas of low pressure due to the fact that air is actually rarefied higher up, therefore low pressure areas, and air is actually dense at sea level, therefore the pressure is higher. So this information here has to do with pressure and the heating of the atmosphere, whereas what we are concentrating on is mainly to do with altitude and temperature. Look at this particular diagram. Perhaps you might have seen this diagram already in our grade 9 booklet. We have an area of Mount McKinley in Alaska. This particular area is located at 63 degrees north latitude. Vertical axis represents the height in meters of Mount McKinley in Alaska. This particular line is very important because this particular line then shows us what we call the snow line. So if we have to look at the snow line, this area here, which has been represented by this red line, indicates the snow line. The snow line is generally the area whereby snow and ice starts to develop as we are going higher up and away from the equator, and the place gets a little bit more cooler, allowing for the snow and ice to develop. Look at the height of the snow line in Mount Alaska. Or not Mount Alaska, but Mount McKinley in Alaska. The height between 2,000 and perhaps 2,500 meters. Let's compare this with Mount Kenya in Tanzania. Where is it located? At the equator, 0 degrees. Look at the height of the snow line, which is the area where permanent snow starts to develop or accumulate. The red line perhaps will help where the snow line is. Look at the height. We go back, we compare the height of the snow line at Mount McKinley in Alaska. Identify the heights then, the different heights. Okay, now to the question, your activity. Can you explain why the snow line at Mount Kenya is higher than the snow line at Mount McKinley? Why is it that the snow line is higher at Mount Kenya than at Mount McKinley? You can discuss. I'll give you at least 2 minutes for the discussion and see if you can come up with an answer to that question. Right on the border of, is it next to Mount Kilimanjaro? Mount Kilimanjaro in Africa. I would have to double check on that one, but here we know that Mount Kenya is at 0 degrees, which is right along the equator. Yes, in Kenya. So maybe with that information we can work on. We can double check to check the other mountains within that region. Okay, I said 2 minutes for us to come up with an answer. Anyone with an answer for that particular question? Can someone then tell us or explain to the class why you think the snow line at Mount Kenya is higher than the snow line at Mount McKinley? Why? Silo, would you have an answer to that question too? There has to be a reason. And perhaps the reasons are associated with what we have covered in our lesson so far.
Maybe because Mount Kenya is at a lower altitude to Mount McKinley.
You're definitely correct. It's not maybe. It's simply because Mount Kenya is at a lower altitude. That means it is located at or closer to where the equator is. And because it's located closer to the equator, it means that you have to go a little bit higher before the temperatures get to below freezing so that ice can be formed. Therefore, the altitude has to be higher. Whereas when you look at the location of Mount McKinley, it is already away from the equator. It is at about 63 degrees north. And because it's away from the equator already, it is cooler in comparison to Mount Kenya. So because it's already cooler, you don't have to go higher up before the ice starts to form. So therefore, at Mount McKinley in Alaska, the height of the snow line is actually lower because of its location or because of its latitude in comparison to Mount Kenya. And that's our answer, and Silo is correct in saying that. Okay, class, that will also bring us to the end of our lesson. But before you go, I'd like you to make note very quickly now of question 3 and 4, as they will be the questions you will be required to complete for your homework. The two questions are: explain in your own words why it is warmer at one time of the year than another. And this has to do with what we've covered on hotter in summer, colder in winter. Number 4, why it is colder at high altitudes but warmer at low altitude. And the second question has to do with what we have covered on latitude. Okay, having made note of those two activities for your homework, that also brings us to the end of our lesson. Class, if you can stand up now. To the pilot teachers, our keyword for lesson 105 is altitude. Good afternoon and thank you, students.